Yes, the last speaker of the seminar is Yongchao Lu from Uppsala University, and he's going to talk about crystallographic elliptic Calogero-Moser system and Seiberg-Witten integrable system. Please start.
Okay. Yeah, thank you very much for the introduction. It's my pleasure to be giving a talk. Today I will talk about crystallographic elliptic Calogero-Moser system and the Seiberg-Witten integrable system. The idea is to introduce and study a class of algebraic integrable systems associated with complex reflection groups and identify them as Seiberg-Witten integrable systems of some Fourier equal to SFTs, in particularly including higher rank Minahan and Mashansky theories with exceptional Fourier symmetries. There is this perfect match between Fourier equal to SFT data and complex reflection group data. This talk is based on joint work with Philippe Aguirre and Oleg Chalik. This paper has appeared on arXiv about a month ago, and I will also try to mention or at least pass something that we are doing. Okay, so let me first give you some outline. First, I will introduce and motivate why do we care about those integrable systems, and then I will go ahead to review for some background in Fourier equal to superconformal field theories and the Seiberg-Witten integrable systems. I will in particularly talk about this particular example. That is the correspondence between A-type elliptic Calogero-Moser system and Fourier equal to star Ewing gauge theory. And then I will go to the main part of the talk. I will talk about my recent work in identifying Zamsov system as a Seiberg-Witten integrable system of deep four theory. This theory is also a superconformal gauge theory with this gauge group and this meta content. And I will go ahead to talk about more general cases, some more general crystallographic elliptic Calogero-Moser system, and identify them as the Seiberg-Witten integrable system of the Minahan and Mashansky's E6, E7, E8 theories. And then I will conclude with some further directions. Okay. Yeah. Then, if you have any questions, just please feel free to stop me. Okay. Okay. So yeah. Let me start with the introduction and the motivation. Yeah, first we know that Seiberg-Witten theory provides us exact solutions to the AR dynamics of Fourier equal to quantum field theories. Yeah, and then the broad goal here is to obtain Seiberg-Witten solution for any given Fourier equal to quantum field theories. But unfortunately, there are no systematic and universal method to construct Seiberg-Witten solution. Nevertheless, people have developed some complementary effective methods. In the early days of the Seiberg-Witten theory, people have considered some answers in terms of hyper elliptical curves and then consider certain consistency checks. People obtained the Seiberg-Witten solution for gauge theories with simple classical gauge groups with matter in the fundamental representation. And later on, people developed some further measures to find the Seiberg-Witten solution with for more general theories with more general applicability. Here, people can consider queer gauge theories, or more generally, some non-Lagrangian theories. Here, people consider some integrable system approach. Here, this is directly linked to the intrinsic integrable structure underlying Seiberg-Witten geometry. And there's also the instanton counting method. And then consider some limited shape equation that will describe the Seiberg-Witten geometry. This method can only be applied to queer gauge theory with unitary gauge groups. So it's relatively limited. Yeah. And then people also consider some stringent method, consider some local Calogero and geometric engineering, some fully quantum field theories, and the geometry of the Calogero will give us the Seiberg-Witten geometry. Okay, so now let me talk more about the Seiberg-Witten integrable system. Actually, just right after the appearance of the seminal work of Seiberg-Witten people have realized the close connection between Seiberg-Witten geometry and the integrable system. But the situation is that people don't know how to find the Seiberg-Witten integrable system in any systematical way. But in any case, people have found two main overlapping sources of Seiberg-Witten integrable systems. That is given a Fourier-equal quantum field theory, people may find some good integrable systems of many body or speed chain type. Here, people have considered the Alpha chain, some Heisenberg spin chain, and some like elliptic Calogero-Moser systems. Actually, just another main sources will be given by the Hengqin system on punctured Riemann surface. This type of integrable system can be given any class S theories constructed in terms of some 6G2,0 theory on punctured Riemann surface. The advantage in considering Seiberg-Witten integrable system is once you find the integrable system, you can systematically extract the Seiberg-Witten solution. Just in the this kind of many particle spin chain system, there are always Lux pairs with spectral parameters, and then you can compute the spectral curve. That will give the Seiberg-Witten curve. And in this Hengqin system case, the K ingredient will be the Higgs field. Similarly, you can compute this spectral curve. That will give the Seiberg-Witten curve. In both cases, there's always a canonical differential. Okay, sorry, here table. Okay, that is they give the Seiberg-Witten differential. Yeah. Okay. And then in this talk, I will mainly consider the so-called Rankine E0, E4, E6, E7, E8 theories. Those theories will arise as word volume theories of multiple D3 brains, proving F theory similarities of Caldera type I0, I0 star, 4 star, 3 star, 2 star. Here actually this A0 theory will stand for Fourier equal to star UN gauge theory, and D4 theory will be just this USP2 gauge theory with 4 fundamentals and 1 antisymmetric hypermultiplies. And there are also these E6, E7, E8 theories. Those theories just the the Rankine version of Minahan and Mashansky theories. Here, this particular notation will really just gives a global symmetry for each of those theory. And then here's the important thing that is for n greater than 1, there is a extra SU2 flavor symmetry that that comes from the isometry in this F theory construction. But there's an issue that is the associated mass parameter for this SU2 flavor symmetry cannot be realized geometrically in this F theory setup. Here in this talk, I will show you that the crystallographic elliptic Calogero-Moser system description can realize the full mass deformations. Okay, so so this is the introduction. So do you have any questions now? Okay, so
I may ask a question.
Okay, yeah.
So the 4D n equals 2 USP2n theory. So
Yeah.
with the 1 anti-symmetric matter, is that 4 fundamental is the maximum number for fundamentals?
If you want to keep this anti-symmetric matter, if you also want to have a super conformal gauge theory, then you just have NF equal to 4.
So, but in 5D you can add to 8, right? So
yeah, in 5D, yeah, in 5D there's no super conformal theory. I mean, just for gauge theory, right? So you can have any number of flavors. So, yeah, certainly if you want to have any like some good 6D origin, then you will consider F less or equal to 8. Yeah, so
okay,
yeah.
so just to be sure, in 4D here the 4 fundamental is the maximum number, right?
Yeah, yeah. Then if you have more, then the theory will be error-free. Yeah.
Okay, okay, thanks.
Yeah. Yeah. Any other question? So okay, let me just go ahead to talk about just to go to review some Fourier equal to SFT data. So a general philosophy here is like the classification and the dynamics of 4D n equal to quantum field theories can be understood in terms of 4D n equal to super conformal field theories and their deformations. And the extended supersymmetry with the eight super charges put just great constraints in the structure of the Fourier equal to super conformal field theories. That tells us that we can really use a finite set of defined data characterize a fully equal to SFT. Here I will give you a list of such fully equal to SFT data. Here we can consider the Coulomb branch spectrum. Here we basically just have a set of positive rational numbers here, and they will be greater or equal than 1. The constraints comes from a inherited bound, and there will be the number of n of that. N is the rank of the Coulomb branch or the dimension of the Coulomb branch, and we also have the Fourier symmetry and the associated the mass parameters. And there are also some other fully equal to SFT data, like conformal central charges, Fourier central charges, and the Higgs branches. But since we are mainly interested in the Coulomb branch geometry, so we will not consider those anymore. We will just focus on those data. Okay. So yeah, and then let me tell you about something on Seiberg-Witten theory. Here we consider the Coulomb branch, which is generally just a copy of n-dimensional complex space, and on each vacuum in the Coulomb branch, we will have a fully equal to a abelian gauge theory with U1 gauge symmetry, and then the main physical data of the low energy physics will include the holomorphic gauge coupling of the abelian gauge fields, and then since there are also some scalar fields, we are also interested in the sigma model matrix, which is actually take some special Kähler structure, and except for the massless fields, we also have some BPS charged particles, and their charges will be valued in some electromagnetic charge lattice, which is also underlaid with the Dirac pairing, and the Seiberg-Witten theory can also give the masses of those BPS particles, which is given in this way. And I also try to just briefly mention those low energy data need to be consistent with the some conditions like EM duality, Dirac quantization, and the singularities and monodromy. Yeah. Okay. So now we come to talk about the connection between Seiberg-Witten's theory and integrability. Actually, Donaga and Witten has shown that the Coulomb branch physics can actually be captured in terms of a family of abelian varieties on the Coulomb branch. Here, this total space will undergo with a holomorphic 2,0 form. Here, lambda will be the Seiberg-Witten differential. And here, we can extract the low energy data from the geometric of the abelian variety fiber will give you the holomorphic gauge coupling of the U1 gauge fields, and the lattice of 1 cycles on billion varieties, and a particular polarization will give us the charge lattice and the Dirac pairing. We also know there's a Seiberg-Witten differential. Then the periods of the Seiberg-Witten differential will give us the central charge of the BPS particles, and then from which we can get the BPS mass. Here, actually, on certain locus on the Coulomb branch, those abelian varieties can degenerate. There will be associated interest in IR physics. Okay. And Donaga and Witten further demonstrated that the Seiberg-Witten integrability is equivalent to the so-called algebraic complete integrability. Here, this total space, along with this holomorphic two form, can be identified with the phase space of certain completely integrable Hamiltonian system. Under this base space, this Coulomb branch will be identified with the space of Poisson commutation Hamiltonians. That will give the action variables in the integrable system, and the abelian variety fiber will give the angle variables of the integrable system. Okay, so here's just a review of the general aspects of Seiberg-Witten integrability. So, do you have any question? So if not, I will just go to talk. Here we will consider Fourier equal to star UN gauge theory and A-type elliptic Calogero-Moser system. Here is the a list of equal to SFG data. Here, since this theory is a Lagrangian theory, we have the gauge group and the matter content. Oh, sorry, yeah. So here the matter is hypermultiply in the adjoint representation of the UN gauge group, and its Coulomb branch operators have spin dimension 1 to 1, and the flavor symmetry of the theory is SU2 when n is greater than 1. When n equal to 1, there's no flavor symmetry. And actually, when the mass vanish, we can find a Fourier. We can find a Fourier equal for UN super Yamir's theory. The theory is super conformal, so there is a conformal manifold which can be parameterized by a exact marginal gauge coupling subject to SL2Z as duality. So this is the n equal to SFG data. Now let me talk about the Seiberg-Witten data. So here we will just talk about this total space and this this Coulomb branch. This Coulomb branch. Here when m equal to 0, this space just take this form, which is just a symmetrical product of 2 torus times c. And when m equal, when we turn on a non-zero mass, then this space will be resolved into the so-called Hilbert scheme of n particles. And the Coulomb branch is just a complex n-dimensional complex space. So here let me just talk about this elliptic Calogero-Moser system. Here is the Hamiltonian. Here we have this kinetic term, and then we have this elliptic potential, which describes the two-body interactions of the particles. Here, this P, it just stands for the Weierstrass P function with the period 1 and tau. So this system is now let me make some comments about the just about this Hamiltonian. Actually, this Hamiltonian has a particular symmetry. It's invariant under the transformations generated by translations and permutations. So those two type of transformations will generate a particular group like this. And actually, this Hamiltonian is, this system is completely integrable in Liouville's sense. That is, there exist n Poisson commuting Hamiltonians of the form like this. Here their leading dependence in the Hamiltonian will be certain symmetrical functions of the momentum. There will be some subleading term that will have some elliptic dependence on the coordinates. So there are n of them. Yeah. So there are n. Yeah. Okay.
So are you mainly considering here the classical integrability?
Yeah, actually here this system is can be naturally quantized. Here it will be modified just a little bit. Here maybe this dependence will be replaced by G times G plus 1, that kind of thing. Yeah.
Okay, so is it known how to solve the quantum theory?
Yeah, I think so. People know a lot of things about this. They know the eigenfunctions of this particular Hamiltonian, and I think people even have certain knowledge about the base ansatz of this system. But
so
I'm not sure.
So it can be quantized by beta ansatz. Is it true?
Yeah, at least for rank 1, I think people. Okay. Oh no, not rank 1. Maybe even for general rank, I saw there are some discussion like beta ansatz for this kind of system, for the A-type elliptic Calogero-Moser system, or maybe.
Because the affine Toda seems you cannot directly use beta ansatz, and I think for elliptic system there are some problems. But okay.
Oh, okay. Yeah, I'm not sure about the true status of that. Yeah. Okay. Yeah, in my impression, there are something like that, but maybe I'm wrong. Yeah. Okay. Yeah. So the integrability of this system can also be established by the existence of some Lux metrics. In particularly, there exists this kind of Lux metrics of sets n, and here, yeah, I would like to say there can be Lux metrics of some other sets, but here we mainly just interested in this one. Here, this Lux matrix take this form. This symbol just stands for the elementary matrix. And then it will have, and then it will depend on momentum and the coordinates, and also couplings, and also depend on the modular parameters and so on, and also spectral parameter. Here, in defining the Lux matrix, we will use this particular quasi-elliptic function, and then with this Lux matrix, we can compute the spectral curve. Okay, so it will have some particular coefficient. Those coefficients will be conserved quantity, will have for polynomial dependence in the Poisson Hamiltonians. So and then let me talk about some properties of this Lux matrix. Here, this Lux matrix has less periodicity property under alpha in the spectral parameter, namely under the shift in periods. This property will tell us the coefficients in the spectral parameter will be elliptic in the spectral parameter. And we will also interested in the singularity structure of the Lux matrix. In fact, there exists a simple pole at alpha equal to 0, and with a residue given by this, it's diagonalizable and with eigenvalues like this. We can learn two things from this. One thing is because of this, just to have simple poles, that will tell us this coefficient function will just be meromorphic with poles at alpha equal to 0. Then that will tell us this coefficient function will just be some elliptic function in spectral parameter. Just another thing is based on the pattern of the residues, we can identify. We can basically learn that this AN type elliptic Calogero-Moser system is equivalent to the GRN Hansen system on torus with certain punctures. When in the vanishing coupling case, there will be no puncture. But if you consider non-zero couplings, there will be a puncture like this. This puncture can be described in terms by this Young diagram. This can basically tells us the patterns of the residues of the Higgs field, which is identical to the residues of the Lux matrix. And then in the end we can match those integrable system description with the Fourier equal to star U-engage theory. This has been done by the Nagel and Docker and Fang. Here we can find that the coupling will be identified with the adjoint mass, and the modular parameter will be identified with the exact marginal coupling, and the commuting Hamiltonians will be identified with the Coulomb branch operator. And the Seiberg-Witten solution, I will not talk about it here, but we know that the Seiberg-Witten solution can be obtained systematically in terms of Witten's elliptic model, and it is can be exactly matched with the integrable system computation. Yeah, okay. So yeah, I will stop here. Yeah, do you have any question? Yeah, if not, I will just go to talk about default theory. Yeah, so I will basically follow the same pattern. I will first talk about the Fourier equal to SFT data. Since it's a Lagrangian theory, I can talk about the gauge group and the meta content. So we have 4 fundamentals and 1 antisymmetric, and the Coulomb branch operators basically the Casimirs of the of USP1. So we have 2, 4, and so on. Based on this meta content, we know the Floer symmetry is spin 8 when times SU2, and there will be some mass parameters and a antisymmetric mass parameters for this SU2. Here, those mass parameters can be identified with the masses of the fundamental hypers. If you take the mass matrix, you can school diagonalize in this way. When the mass vanish, the theory is superconformal. There is a conformal manifold. You can consider the exact marginal gauge coupling subject to SL2ZS duality. Here, actually, there will be a interesting mixture with the spin 8 triality on MI on the fundamental masses. We remark that this antisymmetrical mass is S duality invariant. Okay, so this is the N equal to SFT data. And here is the Seiberg-Witten data. Here, this total space will have different structures depending on depending on the mass parameters. So when the mass vanish, the total space will be a symmetrical product. As long as the antisymmetrical mass vanish, it still be a symmetrical product, but here this orbifold will be resolved in a certain way. But once you turn on the antisymmetrical mass, this symmetrical product structure will be resolved into a hybrid scheme of endpoints like this. Yeah. So just again, this Coulomb branch is still just a copy of n-dimensional complex space. Yeah. So now let me talk about this Zamtsev system. Here's a Hamiltonian. You can find this. It just resemble the A-type elliptic Calogero-Moser system, but now you have more terms. In particular, you have this type of external potential term. There you have 4 terms. There will there will be some half period shifts in this elliptic function, and also there there will be some extra couplings except for this decoupling. Just again, this Hamiltonian will have some symmetry. As before, there will be this symmetry under shapes. this translation symmetry. You also have the permutation symmetry. Besides that, there will be some sign flipping on the coordinates. So you have a larger symmetry here. And also here, let me mention this complete integrability. Again, there exists n Poisson commuting Hamiltonians. Here it takes this form. Its dependence on the momentum is different from the A-type. Here, the momentum always comes in the story like the squares of the momentum. Yeah. So
may I ask a question here?
Yeah.
What's the procedure that you start from a gauge theory? How do you guess, or how do you work out what is the corresponding integrable system? Is there a systematic approach, or you have to do it case by case by some guesswork?
Yeah, I should say there we should have some guesswork here. From my perspective, just mainly some guesswork. Yeah. Previously, people know this model, but I don't know why they didn't identify it as a Seiberg-Witten integrable system. Yeah.
Okay, so this is by guesswork, and then you check that it indeed matches by comparing the spectral curve and other things.
Yeah, kind of like that. But even before you compare the spectral curve, just from the structure of the phase space and the structure of the phase space, you basically learn something. Yeah. Actually, here if we turn off this decoupling, you will find that this Hamiltonian is really just describe and decouple a decoupled system of n particles, right? So yes. Their phase space basically just a symmetric product. So yeah, so I agree. This is basically mainly some guesswork, but there are really you can also find some guiding features.
Okay, and a related question is, what can we learn about Seiberg-Witten theory once you know the corresponding integrable model? I mean, apart from matching the spectral curve, what else can you learn?
Maybe I will mention this at the end of the talk, that there are some future directions that may relate to this. Maybe one thing, if you quantize this system, it may have some relation to the instant partition function and that kind of things. Maybe we can talk about later.
Okay.
Yeah.
Okay.
Yeah.
You can also ask the question.
Yeah.
Do people know the relativistic uplift of this system?
Oh yeah, there are some relativistic model like this. Here, yeah, the story is a little complicated, but so here, this system, we know there's a 1 + 4 parameter, right? If you consider the relativistic version, there's a 1 + 8 parameter system of generalizing this.
Yes, I'll ask this question because I would imagine that the relativistic lift of this integrable model would be corresponding to the 5D n = 1 USP 2n theory with probably nf = 8.
Yeah.
Usually, okay.
Yeah.
Okay. So have you checked that as well?
Oh, that integrable system. Now, I think it can be identified with the integrable system called one digit system. I'm not sure you know it or not.
Not really.
Actually, if you look at that system, you can find 1 + 8 parameters, basically identical to the 5G theory you are mentioning.
Okay.
Okay. That 5G system you are mentioning actually comes from the S1 compactification of E-string theory. So
right.
Yeah, so they are related. Yeah.
Okay, thanks.
Yeah.
Another simple question. So in this model, the Hamiltonian is what's the boundary condition? Is it just periodic?
Oh yeah. Here just I think here is just periodic. Yeah.
So is there any correspondence if you take some open boundary, or there are open and integrable boundaries. Is there any correspondence in the gauge theory side?
For this system, it seems no boundary condition, but actually, if you consider the decoupling limit of this system, consider some total limit, now we realize there you can find some other integrable system, which can be described as some Heisenberg spin chain with the boundary conditions.
I see.
Yeah, so that integrable system will describe a fully USB twin gauge theory with 4 fundamentals, but with no antisymmetric. So it's asymptotically free theory. But that integrable system can have that kind of boundary condition stuff. Yeah.
I see. Okay.
Okay. Yeah. Another question. So here let me talk about the Lux matrix. Here this Lux matrix will have sets twin. So this twin by twin Lux matrix. We have basically the same ingredient like the A type system. And here but here we have some extra ingredient to incorporate the extra couplings. This is kind of wave function. Yeah. So here just like this. And again, there are some nice periodicity condition in spectral parameter. And also we have this type of singularity in spectral parameter. Here we have four simple poles, and we have the pattern of the residues just like this. One particular feature I want to emphasize is the parameters entering the residue naturally will not be the coupling appeared in the Lux matrix and Hamiltonian. They appear in the form of dual couplings defined in this way. So this is a very interesting feature. Maybe I will mention later. Yeah. So just then from this singularity structure, one thing we know that those coefficients will be elliptic function in spectral parameter. Just another thing that will tell us the Hessian, this can be identified with the Hessian system of GL2N Higgs bundle, just living on two spheres with 4 punctures. So when the coupling vanishes, we will have 4 identical punctures. But once we try to turn on the mass, we need to consider this type of puncture. Namely, one of the puncture just need to be modified. So but by this you can have more just incorporate this particular coupling. Yeah. So yeah, then we can match with the gauge theory. So we have the here we can match this coupling with the antisymmetrical mass. We can match the two couplings as the SU2 masses just associated to the punctures, and here we can match the gauge coupling, and then we can match the Hamiltonian and the Coulomb branch operators. Yeah. Okay. Here I will just briefly mention this modular property. Here we can consider the modular transformation. So just consider a modular transformation. Here, the variables we will assign different transformation law. In particularly, we will keep in mind here we need to consider a particular permutation of those couplings. With this taken into account, we can find the Lux matrix and the spectral parameters has some particular modular properties. So the combination of this modular property and this permutation action on the coupling can be interpreted as SL to Z S duality mixed with spin triality. Yeah. So yeah. So how much time do I have? Yeah. So okay. So then actually here we can get more knowledge about this. Try to just try to compute this spectral curve. We can do this for n equal 1 and 2. For n equal to 1, we can get this spectral curve like this. Here will depend on the Hamiltonian and also some elliptic functions. For n equal to 2, it will just a little bit more complicated. It will, but we just need to notice it will depend on the commuting Hamiltonians, and also the couplings, the G couplings, the G2 couplings under U check, and there will be some, yeah, there will be this G coupling. Just so, yeah. Actually, here this integrable system result. Actually, we can get this Seiberg-Witten solution in terms of the Z2 orbifold of Witten's elliptic model. Here we consider a type 2A configuration. There will be some AS5 deformance probing the background with 2 O6 minus orange folds and 46 brains. And then this configuration has an M-theory lift. This background will be lifted into a deformed Z2 orbifold of this T2 times C. And this background will encode these spin-8 masses, and this brain configuration S5 deformance will be lifted into some M5 brains embedded in this background surface. And then this SU2 mass can be introduced in terms of so-called some shift, some affine bundle construction. Yeah, I will not explain that. It's technical. Yeah. And then we can describe this background surface explicitly. Here we are using the invariant coordinates. We can write it in this way. So here we have this background surface. Here we have one form. Its differential will give a holomorphic two form on this background surface. And then there's an ansatz for the curve embedded in that background surface. We use these ingredients, we can solve this curve. We can do this for n equal to 1 and n equal to 2. It just take this kind of simple form. And then this kind of M theory curve can be matched with this spectral curve if we make this identification. We identify x and y with some p function and then we consider the match of the parameters and the modulus, parameter and modulus, and then we can find a perfect match between this spectral curve and the M-Feinberg curve. So okay, so now I'll finish the story for the D4 theory. So I think it's a good point for questions. So if you have any question, so maybe let me just go ahead to some further stories. Maybe I will just finish it in 10 minutes. Here I will consider the Minahan-Meshevsky's E6, E7, E8 theories. First of all, those theories are non-Lagrangian theories, and the Coulomb branch. But those theory has some Coulomb branch operators. Their scaling dimensions will be multiple for M. M is equal to 3, 4, 6. And the Floer symmetry of the theory will be just E6, E7, E8. When n here when n is greater than 1, you will have an extra SU2 Floer symmetry. Those theories are isolated SFGs. There are no exact marginal couplings. Similar to the D4 theory, we can find the structure of the total space of Coulomb branch like this. And the Coulomb branch again, just a copy of complex space. So and then actually there's a underlying complex reflection group structure underlying those theory. Here's a brief introduction about complex reflection groups. So the key point is the key point here is the invariance of the algebra of invariance under those complex reflection groups will be a polynomial ring. So the underlying underlying space of orbits will just a copy of n-dimensional complex space again. The complex the generators of homogeneous invariant polynomials of this algebra of this algebra of invariance will be given in terms of some degrees. Those degrees will be uniquely determined by the complex reflection group. So those complex reflection group has been classified. There will be some infinite families like this, and there are some other exceptional cases. For our case, we also need to consider crystallographic condition. That means there exists an invariant lattice of full rank. So here, the particular complex reflection groups will just be GM1N. N is the rank of the group. M is just associated to the order of reflections. Those ones actually it's also well known as abstract group can be identified with the generalized symmetrical group. Those groups will be generated by this kind of rotations and also by permutations. Here omega is just the primitive roots of unity of order M. And the degree of this GM1N is just multiple of M. And then I want to mention just within this class, there are two non-genuine cases. That is, those ones can be realized as the complexification of some real reflection groups. Here, the relevant real reflection groups will be the Weyl group of A type and B type. Those groups has appeared in the former part of the talk. And if you consider the crystallographic condition on GM1N, that will tell us M can only take a value in 1, 2, 3, 4, 6. 1, 2 has been just those two cases, and then we will have some other cases. Actually, just for this particular group, that lattice will just can be take a particular form. That will depend on particular and the shape of the lattice will take this particular form, and then the orbits of this lattice will just a product of n torus with a particular moduli. When m equal to 1 and 2, this modular parameter is arbitrary, but if you consider m equal to 3, 4, 6, the modular parameter will take some particular meaning. At those we know at those particular modular parameter, the elliptic curve will have some enhanced automorphism group. Yeah. So this is just some background on complex reflection group. So now I want to just talk about the Hamiltonian for the m equal to 3 case. M equal to 4 and 6 will be a little complicated. And again, here we notice it's just a sum of two parts. Here is a two-body interaction part. Here we have some one-body interaction. It's kind of a external potential term. One thing you notice is its dependence on the momentum is not quadratic anymore. The lowest order is the cubic one. So so this really tells us those Hamiltonian system does not admit any natural classical mechanical interpretation. They are complex intrinsically. Yeah. So yeah. So here, yeah. Then I will talk about the symmetry. Here we have this kind of symmetry, except for the common translations and permutations. There's this kind of rotations. And also we have the Poisson commutation Hamiltonians. We notice their dependence on momentum will come as the cubic of momentum. So then we have we can write down the Lux matrix. Just resemble the A type and the B type were in examples of case. Here we have this one particle case and this two particle case. Here we have some new ingredients in describing this Lux matrix. Okay. One thing I want to emphasize is now the dependence on the model parameter is not arbitrary anymore. We need to fix it based on the value of m. Yeah. So now I want to comment that this Lux matrix can be obtained in terms of the elliptic Dunk operator technique. Yeah, and I also want to mention when we consider the residue of the Lux matrix, the coupling will enter in terms of some dual couplings, not just to G coupling directly. Okay, so here just something about the fixed points of the T2 under this particular automorphism. The key point is there will be 3 equivalent fixed points, and their positions will be given in the following data. Yeah. So actually, those particular integrable systems will be equivalent to the Henging system described as the GL-MN Higgs bundle on a 2-sphere with 3 punctures of type like this. If you want to consider non-zero couplings, you need to modify a particular puncture like this. That will introduce one mass parameter. The match. Oh, sorry. Here's some table. Yeah. To match with the field theory, we will match this G as the that SU2 mass, and match the other dual couplings as the E6, E8, E6, E7, E8 mass parameters. In this Henging system, only this particular subgroup will be manifest. And we also match the commutation Hamiltonians with the Coulomb branch operators as expected. Okay, so yeah, so yeah, here is some result on the E6, E7, E8 theories. So if you have any question, just yeah.
Actually, I have a question. So
Yeah.
how do you find this complicated integrable system Hamiltonian?
Yeah, actually, here in this talk, I didn't mention this elliptic Dunk operator technique. In fact, here, once you know the here, the story is like we can write down those elliptic Donkor operators for those complex reflection groups, and then we can use that to compute the Hamiltonian. Yeah. So the Hamiltonian will be some particular some symmetric combinations of the elliptic Donkor operators. For those models, we can actually just reduce the computation down to the one-dimensional cases. We just consider the Donkor operator for the one-dimensional for the rank 1 elliptic Donkor operator, and the computer is a symmetric combination, and then you can find this this Hamiltonian.
So is the Donkor operator known only for the cases you mentioned, or is it known for any GMPN?
In principle, you can get that. It's just a matter to work that out. Now we have no the result for GM1, and for GMPN there are some systematic ways to write that down. Yeah. Yeah. So to answer your question, yes, I think for our GMPN cases, people can write down the elliptic Donkor operator.
I have another question. What's the difference between E6, E7, E8? Did you explain it?
Yeah, for E6, E7, E8, that will on this complex reflection group set, that will be distinguished by the value of m. So when m equal to 3, just E6. When m equal to 4, that will give you E7. When m equal to 6, that will give you E8. Yeah.
Okay.
Yeah. Okay. Yeah. Okay. So let me conclude with some further directions. Here I want to mention maybe some possible relation between Yongchao system and the gauge dynamics. Here we know that default theory is a gauge theory, so we might want to utilize certain is gauge theory description. Here I have certain open questions. Here one thing is one may hope to extract the quantum Hamiltonian from the instant partition function with certain surface operators, just following the gauge-based ansatz approach. And also there are some other so-called gauge origami construction. Maybe from this construction, one can extract some deformed Yongchao system. And then also in the framework of AGT, it looks like this quantum Hamiltonian can be identified with certain differential operator acting on the WCN conformal blocks. And just another question is relating to the classical Hamiltonian. Here we can consider the n=1 deformation, the n=1 deformation of the theory just on a circle. this classical Hamiltonian might be identified with the elliptical superpotential for this system. So yeah, here is another field direction. Here we can consider the degeneration of the Zamtsov system and identify that with the various decoupling limit of the USB2 gauge theory. One thing we can consider is just to decouple some fundamental masses. Here we can expect to get some higher rank Calogero-Douglas theory of H012 type. Here there may be some interesting relation to Penlaway geometry. And then we can also consider decoupling the antisymmetric hyper. Here we can consider some Tada limit. Then there we can find some open spin chain story. Now we can pursue this complex reflection group story further. We can construct those integrable system explicitly, and we actually find some of this can be identified with some Fourier equal to 3 and Fourier equal to 2 and n equal to 3 S-fold theories. Yeah, so this is a direction which we are pursuing now. Yeah, there may be some even interesting questions which we don't know yet. Yeah. So yeah, this is my talk. Yeah, thanks. Thank you for your attention.
Yeah, thank you very much. If you have any questions, please unmute yourself. Well, actually, I have one question. It's related to the host talk. Or is any relation between his talk and your talk? Because you two guys are colleagues.
Who's talk?
Paul Ullman.
Oh yeah. Maybe this F theory story has some connection. But you mean last week, right?
Yeah, that's right. He mentioned overfolding some compact Calabi-Yau, and then he also picked out like M cos 1, 2, 3, 4, 6.
Yeah, I didn't attend that talk, but I think there should be some relations. Maybe one distinction is here we consider the systems with 8 supercharges or more. Mm-hmm. And I think he will be more interested in less supercharges case, right? Yeah, I'm not sure. Yeah. Yeah, maybe his motivation will be more phenomenological. Yeah.
Excuse me, I have a question.
Yeah.
Like these models you consider over here are all like classical integrable model?
Yes.
So you should expect that, for example, you consider the instant and partition function and taking the Nekrasov shattered real element, you will find the quantized version of this.
That's one way. Actually, just those particular model, there are natural quantization, even without considering the gauge theory part. I think here we can even just utility the known quantum description of the system. Maybe just use them to learn some gauge theory story.
Okay, so but usually like there are many like different ways of quantization. So this nature method you just cite is the same as the Nickersoft Shattered-Witten limit, or they're different?
I'm not fully sure about this. It seems for the A-type elliptic Calogero-Moser system, it should be identical to that. My guess is the quantization, the known quantization of the system, is just identical to Nickersoft and the Shattered-Witten story, but I'm not fully sure.
Okay, yeah, thanks.
Yeah.
Any other questions? If not, let's thank the speaker again.